All right, so moving on to 5.3, we're going to talk about the sum and difference identities for cosine. We'll talk about the sum and difference identities for sine and tangent in the next section. But really, a lot of the rest of these identities that we want to prove, they really rely a lot on this very first proof that we're going to go over. So these are what we're talking about here, the sum and difference identities, right? So these ones, so cosine alpha plus beta, right, equals this stuff. So the first thing that I want to convince you of before we actually get going on this is that cosine A minus B is not the same thing as cosine A minus cosine B. And you can plug in values for A and B to convince yourself that that is not true. Here's one, right? If you let A be pi over 2 and let B be 0, then cosine of A minus B would be cosine of pi over 2 minus 0. That's just cosine pi over 2, which is 0. On the other hand, cosine A minus cosine B would be cosine pi over 2 minus cosine of 0. Cosine pi over 2 is 0, cosine of 0 is 1. So that comes out to -1. You can see that you don't end up with the same result, right? So the trig functions, generally speaking, don't behave very well in terms of distributing across multiplication, addition, subtraction, division. It just doesn't work. So you can't distribute the cosine across that subtraction. So cosine A minus B is not the same thing as cosine A minus cosine B, but here's what it is equal to. So cosine A minus B is cosine A times cosine B plus sine A times sine B. And you might think, well, where in the world do you come up with that? So I'm about to prove it to you. I'm going to redraw this picture kind of one piece at a time so it's not so overwhelmingly confusing. But so we'll give ourselves a little unit circle. Or I guess it doesn't have to be a unit circle, but just a circle here centered at 0, 0. And so I'm going to choose a point over here, and we'll call this angle A. Alright, so there's angle A. And then we're going to choose another point over here, and we'll call this angle B. And then I'm going to give myself one more angle that's supposed to represent A minus B, right? So this is supposed to represent A minus B. And by the way, I'll call this point R, and I'll call this point Q. I'm also going to label this the origin O, and maybe I'll label this point, the point 1, 0, S, right? So S equals 1, 0. Okay, so a couple things to note about this. Note that point P, so if this is the unit circle, then the point P is just, so remember this is angle A right here, so point P is just going to be cosine A sine A. Okay. I guess I should say P equals that, right? Point Q, well that's a little bit harder. Let's maybe do point R. Point R, right, this is angle B. This is angle B right here. So R is going to be cosine B sine B. So Q, well this is angle A minus B. So Q is cosine A minus B sine A minus B. Okay. Now, another thing to note, and this is a big one, is that angle POQ is equal to angle QOS. So let's see if we can figure out what angles we're talking about, right? So angle POQ, right? So we're talking about this angle right here. And this may not be very clear from the way that I've drawn the picture, but POQ is the same thing as QOS, right? That's definitely not clear from the way I've drawn the picture, but they are the same thing, right? Because this angle right here was supposed to be angle A minus B, So QOS is just A minus B. On the other hand, POQ, well, P is angle A, and then this is angle B. So that means this angle, to get from here to here, oh, that's why it's not making sense. It should be POR. So POR, not POQ. So sorry, POR. That makes a little more sense. That looks more convincing. Anyway, POR, this is angle A minus angle B, right? So it's also just A minus B. So those two angles are the same. Now, since those two angles are the same, that means their secants are the same. In other words, the line going from P to R is the same distance as the line going from Q to S, right? So, therefore, segment PR is equivalent to segment QS. Okay? So then finally, if you think, well, what is the distance from P to R? Well, we can use the distance formula for that, right? The distance formula is going to be from P to R. So it's going to be x2 minus x1. So that's cosine B minus cosine A squared plus y2 minus y1. So that's sine B minus sine A squared, right? So that's segment PR, and then segment QS is going to be, well, what's the distance from Q to S? Remember, S is the point 1, 0. So the distance from Q to S is going to be, it's going to be 1 minus cosine A minus B squared plus 0 minus sine A minus B squared. Okay. And believe it or not, that's it, right? That's the relationship. So if we solve this thing now for cosine A minus B, we're going to get the desired relationship. Let me just take it a couple steps so that you can maybe see it. But first of all, if we square both sides, that'll get rid of the square roots. So I'm not going to write the square roots anymore. And then in the second place, I'm going to go ahead and FOIL these out. So I'm going to have cosine squared B minus 2 cosine B cosine A plus cosine squared A. And then I'll have a similar thing here. It's going to be sine squared B minus 2 sine B sine A plus sine squared A, okay, equals, this stuff is going to be, if I FOIL that out, I'm going to have 1 minus 2 cosine A minus B plus cosine squared A minus B. And then here, 0 minus sine A minus B is just negative sine A minus B. And then when you square that, you're going to get a positive sine squared A minus B. Okay, so we've got a bunch of Pythagorean stuff that we can cancel. Like cosine squared plus sine squared is just going to be 1 here. Also, I've got a cosine squared B and a sine squared B, so those are going to combine to give me 1. So maybe I'll do this in a different color so you can see what I'm saying a little better. So when I combine these two, cosine squared plus sine squared, that's going to give me 1. And when I combine these two, cosine squared A plus sine squared A, that's also going to give me 1. So altogether I'm going to get a 1 from the greens and a 1 from the blues. That'll make 2. Minus 2, I don't know why I wrote it so close, let me say 2 minus 2 cosine B cosine A minus 2 sine B sine A, okay, equals, and then on the right hand side, this one plus that one will make a 2 minus 2 cosine a minus b. Okay, so now it should be really pretty clear, right? But we're almost done at this point, so we might as well finish the proof. We subtract 2 from both sides. So we're going to have negative 2 cosine b cosine a minus 2 sine b sine a equals negative 2 cosine a minus b. And then go ahead and divide through by negative 2 and you've got it, right? So you've got cosine b cosine a plus sine b sine a equals cosine of a minus b. And that was exactly what we set out to prove, right? We set out to prove that cosine a minus b is cosine a cosine b. Here I just rewrote the order, plus sine a sine b, right? So that's that. Most of the rest of the identities on your trig identity sheet, so most of the rest of these, believe it or not, they all follow from this fact, more or less. Okay. For example, cosine a minus b is this stuff. What's cosine a plus b? Well, that turns out to be the same thing as what we had up here, but the sign in the middle changes, right? So cosine a plus b is cosine a cosine b minus sine a sine b. And here's the proof for that. So the proof is really simple, right? We can just call cosine a plus b, that's just going to be cosine of a minus negative b. And now you can apply this fact, right? You can say, okay, well, so then that's just going to be cosine a cosine negative b plus sine a sine negative b. And then remember, cosine is an even function, so cosine negative b is just cosine b. Sine is an odd function, so sine negative b is negative sine b. So I absorb this negative sign here. And that's that one. So let's practice applying those two facts now. So let's find the exact value. Of cosine of 75 degrees. Okay, 75 degrees is not one of those special angles that we have memorized, right? So we know 30 degrees, we know 45 degrees, we know 60 degrees, and of course the quadrantal angles 0 degrees, 90 degrees, but we don't know cosine 75 degrees. However, we can rewrite this in terms of two angles whose values we do know, right? So 75 degrees, we could call it 90 minus 15, except we don't know 15. Or we could call it 30 plus 45. We know 30 and 45, right? So I'm going to call this cosine of 30 degrees plus 45 degrees. And then I'm going to apply my sum identity for cosines, right? So the sum identity says that this is going to be cosine 30 degrees, cosine 45 degrees, minus sine 30 degrees, sine 45 degrees. So the sign is opposite. And by the way, let me point out on your formula sheet, notice that when we're writing out the sum and difference identity for cosine, here we have a plus or minus, and here we have a minus plus. That's because the sign changes. So if you're starting with alpha plus beta, it becomes a minus sign over here. If you're starting with an alpha minus beta, it becomes a plus sign over here. Anyway, so the rest of this is just knowing the values of the trig functions, right? So cosine 30 degrees, for example, is root 3 over 2. Cosine 45 degrees is root 2 over 2. Sine of 30 degrees is 1/2, and sine of 45 is root 2 over 2. So you get root 6 over 4 minus root 2 over 4. Or if you like, you can just call it root 6 minus root 2 all over 4. Either way is fine. But that's the exact answer. Okay? Let me give you another one kind of like that. So we'll do cosine of pi over 12. So this time we're working in radian mode, but go ahead and give the video a pause and see if you can work that one out. Okay, so here's my solution. I think you could go about this in multiple ways. So I know, for example, that the difference between pi over 4 and pi over 3 is pi over 12, but also the difference between pi over 4 and pi over 6 is pi over 12. So so you could use either one. I'm going to call this, I'm going to do it that second way. I'm going to call this cosine of pi over 4 minus pi over 6. Right? Because if you subtract these, you would get a common denominator of 12. Here you'd multiply by 3 and get 3 pi over 12. You'd multiply by 2 and get 2 pi over 12. 3 pi over 12 minus 2 pi over 12 is pi over 12, right? Okay. Now I can apply that identity we just proved. This is going to be cosine pi over 4 cosine pi over 6 plus sine of pi over 4 sine of pi over 6. And then we can evaluate those, right? Cosine pi over 4, root 2 over 2. Cosine pi over 6, root 3 over 2. Sine of pi over 4 is root 2 over 2. And sine of pi over 6 is 1/2. So this is almost the same as what we got before, right? It's root 6 over 4 plus root 2 over 4. Or if you prefer, you can call it root 6 plus root 2 all over 4. So kind of interesting. You could apply these rules in reverse as well. So let me show you what I mean. Let's say that you had something like cosine 27 degrees, cosine 63 degrees, minus sine 27 degrees, sine 63 degrees. So this looks awfully familiar, right? It's like these angles match, right? You've got cosine, cosine, sine, sine. So it seems like this is a difference formula for cosine, right? This is just the right-hand side of the difference, or rather of the sum formula for cosine. So this is going to be cosine of 27 degrees plus 60 degrees. Okay, so I'm just using that same rule but in reverse. And 27 plus 63 is 90. So this is cosine of 90 degrees. Cosine of 90 degrees is 0. So you should just get 0. It would be interesting. You should plug that into your calculator and verify that you do in fact get 0 there, but it should be 0. Okay. So another thing that we can prove now that we have this difference identity for cosine is we can prove this this cofunction identity, right? That cosine of 90 degrees minus theta is just sine of theta. That's something that we've talked about in the past, but I don't know if we ever gave a formal proof. I think we talked about it for acute angles theta, but we never proved it for any angle. But it is true for any angle, and now the proof is really easy. Okay, so here's the proof of that. Cosine 90 minus theta is just cosine 90 cosine theta plus sine 90 sine theta. Cosine 90 is 0, sine 90 is 1. So this just comes out to sine theta. Okay. Let's practice applying that. So we're gonna solve some trig equations here. So let's find one solution. So let's find one solution to sine theta equals cosine of 12 degrees. Okay, so the way I'm going to work this out is I'm just going to use that cofunction identity that we just looked at, right? I'm going to say sine theta equals, instead of cosine of 12 degrees, I'm going to call this sine of 90 degrees minus 12 degrees, right? Cofunction identity there. So then sine theta is sine of 90 degrees minus 12 degrees would be 78 degrees. Okay, well, if sine theta equals sine of 78 degrees, then one obvious solution would be theta equals 78 degrees, right? Okay, so that's how you deal with those. Let me give you one more. we'll do cosecant of 3 pi over 4 equals secant x. Okay, so same idea here. You can use a cofunction identity. I'm just going to call this secant of pi over 2 minus 3 pi over 4, right? 90 degrees minus theta equals secant x. Pi over 2 would be 2 pi over 4, right? 2 pi over 4 minus 3 pi over 4 is negative pi over 4. This is going to be secant of negative pi over 4. And in fact, secant is an even function, so I know that secant of negative pi over 4 is the same thing as secant of just pi over 4. That gives us an obvious solution, right? X is pi over 4. I guess you could have also said x equals negative pi over 4. That's another solution, right? We were only asked to find one. There are infinitely many. Okay, so negative pi over 4 would also have worked, but okay, but there you go. How many more examples do I have? I've got 1, 2, 3, 4 more examples. Okay, so here's something else we can do now that we've got this tool, right? So we can write cosine to 270 degrees plus theta as a trig function of theta alone. In other words, we want our argument to just be theta, not like, you know, theta plus something or 2 times theta or whatever. We just want the argument to be theta. So how can we do this? Well, obviously by using the sum identity that we just derived a second ago, right? So this is going to be cosine 270 times cosine theta minus sine of 270 sine of theta. Cosine of 270 degrees is 0. Sine of 270 degrees is negative 1. So this is 0 plus sine theta. I'm not sure why I put a little parenthesis there, but there you go. A negative and a negative make a positive, right? So this is just sine theta. So there you go. That's kind of interesting, right? Cosine of 270 plus theta is just sine of theta. Okay, here's a more challenging one. So let's find cosine of s plus t and cosine of s minus t if cosine s equals negative 8/17, cosine t equals negative 3/5, and s and t are both in quadrant 3. Okay, so this might seem a little bit overwhelming. At first, it's helpful to start writing stuff down. Like if I want to find cosine of s plus t, well, what is it? What's really what is entailed there, right? Like what do I really need? So cosine s plus t is cosine s times cosine t minus sine s times sine t. So what do I need? Well, I need cosine s, I need cosine t. I was given both of those values, but I also need sine s and sine t, and I don't have those yet. So so I think I'm going to have to use the fact that cosine s is negative 8/17 and that cosine t is negative 3/5 to solve for sine s and sine t. You can use Pythagorean identities for that, or you could draw a little right triangle and solve for the missing side. I'm just going to use the Pythagorean identities since we're in the Identities chapter. I figure we should use some identities. So let's solve for sine s. So I know that sine squared s plus cosine squared s equals 1. Well, that means that sine squared s plus negative 8/17 squared equals 1. So sine squared s. Oh shoot, what's 17 squared? 289, I think. 17 squared, 289. So this is 64 over 289, and then I'm going to subtract that from 289 over 289. So let me see, 289 minus 64, 225. Oh, that's so nice, right? So you get 225 over 289. This was rigged, right? Okay, so then you take the square root, and you get sine s equals 15/17. Beautiful. Okay, so there's sine s. Right, so I have cosine s, I have sine s, I have cosine t, now I need sine t. So I'm going to do the same thing with angle t. Right, so I'm going to say sine squared t plus cosine squared t equals 1. So that implies that sine squared t plus negative 3/5 square. Oh, that, I'm not even going to finish it. We know that sine. Oh, hold on a second. Wait, I may have made a mistake up here. So s and t are in quadrant 3, right? When I took the square root, I needed to have a plus or minus sign, so I needed to choose, is this going to be positive or negative? If we're in quadrant 3, this is going to be negative, right? So I need to have a negative sign there. My apologies. Maybe, let me do this so it's more clear. I've got to choose the negative one because we're in quadrant 3, right? Okay. Well, anyway, finishing this up, if cosine is 3/5, sine's got to be 4/5, right? And since we're in quadrant 3, it's going to be negative 4/5. So you could finish up with the whole Pythagorean business here, but I know that you're going to get sine t equals negative 4/5. That's what we should get for sine t. Whoops, sine t. So now I have all the pieces that I need in order to figure out cosine of s plus t. Right? It's cosine s, cosine t, minus sine s, sine t. So that's negative 8/17 times negative 3/5 minus negative 15/17 times negative 4/5. And the rest is just simplifying that mess. 8 times 3 is 24. 17 times 5 is whatever it is, 85. Okay, and then minus 15 times 4 is 60. 17 times 5 is again 85. See, this is when I miss live classes, because you can call me on my arithmetic mistakes if I make them when we're live, but if I'm just recording this video, I sometimes don't realize when I've made a mistake. 24 minus 60, negative 36. So negative 36 over 85. And there you go, right? So there's cosine of s plus t. We were also supposed to find cosine of s minus t, but hopefully you can see that that's practically done already, since cosine of s minus t is just cosine s cosine t plus sine s sine t. So it's just exactly the same as what we did a second ago, but we're going to change this to a plus sign. Okay, so that's 24/85 plus 60/85, so that should be 84/85, which is a very trig-like answer to get. Okay, that was a doozy of a problem. Well, let me give you two more, and then we'll call it a day. So let's practice verifying some trig identities now that we have a few extra tools in our toolkit. So let's verify that secant. Oh, this is easy. Secant pi. I'll let you pause the video and see if you can do this one. So see if you can verify that secant of pi minus x is negative secant x. Oh, maybe it's not as easy as I thought originally. If it was pi over 2, well, it wouldn't even be true if it was pi over 2, though. Well, anyway, here we go. I'm going to change these to cosines. Oh, do I really want to do that? I think I have to. All right. Alright, so this is going to be cosine pi, cosine x minus sine pi, sine x. That's not bad. That's really not that bad. Okay, cosine pi is -1, and sine pi is 0. Oh, there you go. There it is. Yeah, so that one was easy. It was easy. Okay. Here's another one. 1 plus cosine 2x minus cosine squared x equals cosine squared x. Wow, can that really be true? That's interesting. This is 1 no. I was going to say it's 1 minus cosine x quantity squared, but that's not right. That's not true. Well, okay, so I'll give you a hint on this one. Think of cosine 2x as cosine x plus x, and then apply the sum formula. So I'll give you a second to see if you can work that out. Okay, so here I go. So it's going to be 1 plus cosine x minus sine x sine x. Right? So I'm just breaking this thing down here. Okay? And then minus the cosine squared x. So that's 1 plus cosine squared x minus sine squared x minus cosine squared x. The cosine squared and the negative cosine squared will cancel. And then that's a Pythagorean identity, right? 1 minus cosine squared is, or 1 minus sine squared, sorry, is cosine squared. And that's that one. Okay, so these sum and difference identities could come in handy for verifying other trig identities, and you'll see that quite a bit as we move through the rest of the chapter.